It's a great pleasure today to have Anna Rosen visiting us. Anna was born in Los Angeles, California, and while working a full-time job after high school, she attended night courses at a community college at Los Angeles Peace College to complete her transfer requirement to pursue a degree in physics. After this unusual start, she transferred to the University of California, Berkeley, where she obtained her bachelor degree in physics and astronomy in 2009. Afterwards, she attended the University of California, Santa Cruz, where she received her PhD in astronomy and astrophysics in 2017, working with advisor Mark Rumholtz and Enrico Ramirez Ruiz. So during her time at Santa Cruz, she received a National Science Foundation Graduate Research Fellowship. She received an ARCS Foundation Fellowship and also an American Association of University Women American Dissertation Year Fellowship. From 2017 to 2020, she was a NASA Einstein Postdoctoral Fellow at the Institute for Theory and Computation at the Center for Astrophysics at Harvard-Smithsonian. And she is now currently a postdoctoral fellow in the same place as CFA. When not doing science or living through a pandemic, as everybody else got used to doing the last year, Anna enjoys CrossFit, indoor rock climbing, and hiking. She is also an advocate for diversity, equity, and inclusion issues in astronomy and academia, and has participated in many outreach activities such as the LAMAT program at the University of Santa Cruz, the Benneker Institute at Harvard that provides summer astronomy research opportunities for undergraduate students from non-traditional backgrounds. So with that said, again, I would like to welcome Anna, and I will also remind people that if you have any pressing question related maybe to clarification during the talk, you're welcome to use the chat, and I'll forward the question to Anna. Otherwise, for general question, I will suggest people to wait until the end, and then we will have a long Q&A session. So with no further ado, I'll pass the control to Anna. So feel free to start whenever you're ready.
Great. Well, thank you so much. I didn't really realize all that would be read out when I wrote it. Yeah, so thank you for inviting me to give the colloquium today. I'm really excited to talk about the research I've done over the last several years. And most of my research focuses on massive star formation. And a lot of that is motivated about the importance of stellar feedback, because massive stars, even though there's not so many of them, they're highly outnumbered by low mass stars. They strongly contribute to the energetics and momentum input to galaxies in the interstellar medium. And so they have huge impact in all areas of star formation and galaxy evolution. So today I'm going to talk about how massive stars are born and focus on how different modes of stellar feedback limits the growth of massive stars and affects their surroundings. Oops. Okay, so first, like I mentioned before, I always like to start with showing my favorite giant H2 region. This is 30 Doradus in the Large Magellanic Cloud. So an H2 region is basically a swept up shell of material that is being expanded due to the impact of stellar feedback. We normally think of it as photoionization, basically ionizing neutral hydrogen. It heats up the gas and it pushes on the surrounding gas. And so feedback essentially pushes material away from the star itself. In the context of star formation, we also refer to H2 regions to any type of region that not only contains photoionization, but feedback from other mechanisms. And so this is a great example because 30 Doradus is one of the nearest, most massive star clusters to us. And is highly well studied. And this is a great picture because it kind of shows how the interplay of different feedback mechanisms strongly affect the gas that surrounds these star clusters. So here, 30 Doradus contains many stars. However, near its center is this massive star cluster called R136, which is about 2 or 3 mega years old. And what I'm showing here is a composite image of different wavelengths of light from Chandra, Hubble, Spitzer, et cetera, showing how showing how feedback kind of affects different ranges of material within this H2 region. So for example, we see that in the yellow here, this is the coal gas that's illuminated by the young stars. So this is what's known as like the direct radiation. So the radiation from itself that's being absorbed by the surrounding dusty gas. That dust is heavily opaque and absorbs a lot of that radiation, heats up, and then re-emits in the infrared, as we see here, more spread out. And that's because this dust acts as a thermal emitter. And so you have this extra component of radiation pressure that kind of gives you a radiation boost in these star forming environments. And then finally, with the X-rays, what we're tracing here is this hot shock heated gas from the fast stellar winds from the star. And so basically these stars are very bright. And so they launch stellar winds, strong and fast stellar winds from their surface that can collide with the surrounding ISM or collide with winds from nearby stars and shock heat gas to millions of degrees Kelvin that then adiabatically expands like a piston. And so as you can see here, even combining all this information together, stellar feedback is a very messy process. And it turns out that stellar feedback still remains as one of the largest uncertainties in both star and galaxy formation, because stellar feedback inhibits gravity, to reach its full potential. If stellar feedback was not a thing, then you would expect that most of this gas would form stars pretty quickly. But the heating and the momentum injection by stellar feedback actually makes star formation inefficient. Now, like I mentioned, stellar feedback is dominated by massive stars. But if we look at what's known as the stellar initial mass function, or the IMF, which kind of just, if you look at a population of stars, how many stars of a given mass do you expect to have? So it's just kind of like a probability function. You see that for low mass stars, most stars are at low masses. So with massive stars, I'm talking about stars that are 8 solar masses or above that will end their lives in a supernova explosion. So if we look at massive stars and integrate over that, over the entire stellar population, you find that only about 1% of stars and galaxies are massive. But if you look at the energy output, or in this case, right now I'm just looking at the radiation energy output. So this is showing the main sequence, or the 0-age main sequence. So once the stars hit the main sequence, what their luminosity is, and you integrate over the energy output over that stellar population, you find that even though massive stars contribute to 1% of the number of these stars, about 97% of the total energy emitted from the stellar population comes from massive stars. So they're rare, but they dominate the energy injection and of the Milky Way and other star-forming galaxies. And so I like to think that massive stars are the 1% of the universe, and that Bernie does not like massive stars. So another really nice illustration of why massive stars are so important, if we look at our nearest neighbor, Andromeda, and we look at the ultraviolet light, we see that in the densest regions, the spiral arms of this galaxy, you see a lot of this ultraviolet light, and that's from massive stars because they have really hot surfaces. So they emit a lot of radiation at ultraviolet wavelengths. Now, these spiral arms are very dusty. And so again, we can look at the infrared light. And this infrared light traces the radiation that's emitted by the cool dust that's illuminated by massive stars. And when I say illuminated, this dust absorbs a lot of the radiation from the stars and then again re-emits. So similar to the picture I showed before, but on bigger scales. And so we see that star formation, at least in star forming galaxies, or well, star formation occurs in star forming galaxies and not the other way around. You see that massive stars dominate, again, the energy output in such galaxies. And so they have important implications. So like I mentioned before in the first slide, feedback from massive stars come in a variety of mechanisms. The first is radiation, and this is in the form of ionizing radiation that ionizes neutral hydrogen and other elements and heats up that gas so that you can yield H2 regions that then expand due to gas pressure. Also, because also the dust and gas will absorb radiation at other wavelengths. So for example, in star forming environments, they're very dusty. And like I mentioned before, the dust is very, very opaque to a lot of the light from those stars. And so we have another contribution that's due to the direct injection from radiation from stars, and also that dust enhanced radiation pressure. Likewise, because these stars are very hot, they give off these fast isotropic stellar winds, and these winds leave the surface, collide, and yield really hot gas that can then expand. Also during the formation of stars, due to the fact that they're accreting from an accretion disk, these stars launch these magnetically launched jets, so protostellar outflows. And so this is important during the formation timescale of the stars. And these two, radiation and stellar winds, are more important when the star is bright enough and hot enough, for example, to launch stellar winds. And radiation, because the luminosities of these stars are so high, has a huge impact. And then finally, at the end of their lives, they undergo supernovae explosions. And this also injects a quick burst of energy in their environments. Now I'm going to focus on these three mechanisms throughout my talk. And because all three of these can act during the formation phase. And so one thing is that stellar feedback can actually halt accretion onto stars. So accretion is just gravity bringing matter to the onto the stars. And if you can think of gravity wants to push stuff in, whereas feedback wants to push stuff out. And so if feedback is strong enough, you can overturn the accretion flow. On larger scales, in the context of star clusters, the combination of all these feedback effects can actually eject gas from molecular clouds. And so that limits stellar feedback leads to these low star formation efficiencies observed in galaxy clusters. And you can see here in NGC 3603, you have this centrally concentrated star cluster, and feedback has ejected most of the gas from that star cluster. And this leads to very low star formation efficiencies. Star formation efficiency is just the total mass of stars divided by the total initial amount of gas that can be supplied to make stars. And so that varies between 1 and 10% in these types of molecular clouds that host massive stars. And then on larger effects, stellar feedback, like I said, it leads to low star formation in molecular clouds. Overall in a galaxy, that means that the galaxy itself has inefficient star formation. And then if feedback or like gas that is ejected from these star forming sites can be ejected from the galaxy, you can also launch galactic winds. So with M82 here, you can see in the red, you have these outflows like due to stellar feedback. And then again, we can look at the different wavelengths, measuring these different feedback components, where we look at a lot of dust is being, and therefore gas is being ejected from this hot material that's generated by supernovae and X-rays, supernovae and stellar winds. So hopefully I convinced you that stellar feedback is important from the size scales of stars all the way up to galaxies. But also the field has really been paying a lot more attention to this. So as you can see here, how much the field has grown. And I want to mention, these are only articles that mention stellar feedback together. And which means it's not even taking into account individual processes. It just depends on the type of language people use. So I'm sure this number is a lot higher. And because stellar feedback is dominated by massive stars, it's really important to understand how they form. And that's the focus of my research and what I will talk about today. So the first thing is, well, how do massive stars form? Do they form like low mass stars from the collapse of individual cores of material, or do they form in a more dynamical process? So currently there's two main competing theories that have try to understand how massive stars can form. And that's just because feedback is so great that you don't expect to form stars, let's say greater than 20 solar masses. So the first is the core accretion model. And the idea is that you have these infrared dark clouds, these molecular clouds, and the infrared dark because they're very dusty, very dense. And you expect that these clouds will collapse to form these massive cores, that these cores themselves are supported either by magnetic fields or supersonic turbulence, or a combination of both, meaning that the pressure due to motions within the cloud is supplied by random turbulent motions more so than thermal pressure, and that leads to larger cores. However, the requirement is that these cores are virialized, meaning that they're basically bound, and so that they can collapse. However, when you look at the virial parameter of a large number of cores and clumps, you find that they're mostly subvirial. So that requires the existence of stronger magnetic fields, which now a lot of measurements, or a lot of like AMA and other radio observations, are trying to understand the magnetic field structure and also strengths of these objects. However, one of the problems with this is, like I mentioned, is we don't have a large enough sample of knowing what the actual strengths of magnetic fields are in these cores to confirm this theory. The next possibility is what's known as competitive accretion. And the idea here now is that that the cores that you build up low mass cores due to genes fragmentation, and that's just kind of like the gene's mass. So depending on the density of the gas, so this is quite dense, so it can be roughly order half a solar mass or so. And this mass scale is set by the thermal pressure of the gas. And then because, due to the cluster potential, mass will flow down to these sites of massive star formation, and the accreting massive stars will basically steal mass from other stars. And so you tend to build up these massive stars in the cluster potential. And you see that here based on, here's an example, STC 13, where you can see the velocity gradients are increasing towards this center, this filamentary structure, suggesting that that stars can continue growing through accretion. I think in the last several years, especially with AMA, we have seen that it's a more complicated picture than those two. My opinion is probably something more intermediate, or like more of a compromise between those two theories. And this is a nice example I like to think about, because this is a massive clump where that has fragmented into many cores, as seen by ALMA, looking at the dust continuum. And what they find is that, they look at this one specific core, ALMA1 core, which has a mass much greater than the gene's mass. It's about 12 solar, or sorry, yeah, it's about, I believe, 12 solar or 18 solar masses. Shows no star formation, so it hasn't collapsed yet to form stars, and it's actively accreting. So this means that you could have more massive cores, but this is subvirial. So unfortunately, they don't have the magnetic field strengths, but this would require quite a strong magnetic field. And so since this core is actively accreting material, it will grow within a certain time scale and can eventually during that period collapse and form stars, and maybe while it's actively accreting. A latest scenario with that, this is a paper I was on with Adam Avison, where they looked at this molecular clump, again, using ALMA and other observations. They measured, this system here has two massive protostars. They're very bright. And what they find is that massive star formation is quite dynamic. So as these stars are growing, you have these filamentary structures feeding material to the stars. And the accretion rate onto this clump that hosts these two protostars is, approximately the accretion rate onto the stars themselves. So I think it's more of a dynamical picture where you could have these more massive cores, and those cores can continue feeding as these stars form. Likewise, we do see a lot of diversity in these clumps that massive stars form in. And that's just because massive star formation is a multi-scale, multi-physics problem that relies on magnetic fields, turbulence, gravity, and feedback. And so those properties affect the fragmentation of these cores. So here, this is a variety of sources within 6 kiloparsecs. That are bright enough where the stars should be massive, the protostars should be massive. And Ruther et al, looked at the radio emission from these clumps to look at the fragmentation properties. And they find that the fragment population is very diverse. So there's not quite a simple picture. So you have fragmentation happening at all scales. Some don't, some of these clumps aren't fragmenting. Some of them fragment up to, 20 subclumps or cores. And so it's quite a diverse picture of how such stars form. So I wanted to give some motivation about kind of like where we're at with understanding the observational side of massive star formation. There's been a lot of progress over the last several years, especially due to ALMA and other interferometers and radio telescopes, because you can look through the dust with longer wavelength observations. And so my concern too is to understand how feedback itself actually affects the accretion onto these stars. So first, the structure of my talk is to kind of go in order of these different feedback processes, where it's to study, one at a time, where we do more simulations with increasing complexity to be able to see how these different feedback processes add up to increase understanding of massive star formation. So first, I want to talk about radiation, which since the 70s was thought to be the most important feedback mechanism in massive star formation. And that's just because these stars get so bright as they're actively accreting that you would expect, once the star becomes massive enough, radiation pressure is strong enough to just blow material away. And so you shouldn't attain masses more than 20 solar masses. And this analysis is based off a simple, like, spherical 1D model, where you just compare the gravitational force to the radiative force. And here for the radiative force, I'm including both contributions from the momentum injected, so that's L, the luminosity of the star divided by C, from the star itself. But because these form in dusty environments, you also have this trapping of this enhancement in radiation pressure due to the fact that the dust will absorb the radiation from the star and then re-emit. And so you can have this additional component, additional scatterings and absorptions of dust. And as the star forms, a simple approximation is that the solar luminosity should go as the mass cubed. And so that means that these stars get bright very quickly. And so if you just take the ratio of the two, that's known as the Eddington ratio, we can get an idea of when radiation should halt. And so under the simple 1D model, early work, said that stars above 20 solar masses should not form. Well, we know this is definitely not true. So going back to 30 Doradus, this shows the IMF from a recent paper showing what the initial mass function they expect from 30 Doradus by looking at the stars in this H2 region. And they find that they expect stars as great as 200 solar masses might have formed, and that's 10 times as great. So that means that radiation pressure in the simple picture I presented is not responsible for terminating the maximum stellar mass, at least up to 200 solar masses. So, that means that we need to look at this in a more complex way. We need to look at it in a multidimensional way. So one way to overcome this radiation pressure barrier is that you can have an anisotropic accretion flow. So such as by an optically thick accretion disk that can bring material to the star along the equator, for example, and then radiation can launch material away along the poles of the star. However, studying this in detail is very difficult observationally, and that's just because, like I said before, massive star formation is very rare. A lot of the sites where massive stars form are far away, and it's hard to kind of see through the dust and see this in great detail. So one way that we can look at the physics and try to understand the physics of what is responsible for how massive stars form is to turn to numerical simulations. So this requires us to model massive star formation using multidimensional and, of course, radiation hydrodynamic simulations, because radiation pressure is very important. So to do this, as I showed before in a slide, one of the slides a few slides ago, I mentioned how it's not just as simple as the radiation field from the star itself. It's the surrounding dusty material also impacts radiation pressure in star forming environments. So during my PhD, what I had developed was a new hybrid radiation scheme to be used in numerical simulations. And the first is we use adaptive ray tracing for point sources, so stars in our case. So we just shoot rays from the stars and we solve the radiative transfer equation exactly along these rays. And that adds energy and momentum to the dusty gas. And so we use what's known as a moment method, which is just an approximation to the radiative transfer method, which is cheaper than and makes these simulations doable than solving the radiative transfer equation for millions of cells or even billions of cells. And then we just combine those two components. And this is really important because, so this, I'm showing the dust opacity here. The dust opacity at these high wavelengths inherent to the radiation fields from massive stars can increase by orders of magnitude. And so we really want to be able to capture the multi-frequency dependence of radiation absorption onto dust grains. And then we can simply do that with this adaptive ray tracing. So this was added to Orion 2, which is a AMR, so adaptive mesh refinement code, where we basically have a Cartesian grid, and certain areas can then be refined on areas like density, velocities, et cetera, so that we can actually go from size scales of, let's say, sub-parsec down to AU size scales to run these simulations, because star formation ranges many orders of magnitude. And a code like this is just solving, so the radiation hydrodynamic equation is just solving the conservation equation. So the conservation of mass, momentum, energy, and then also radiation energy. And I won't go into all the details because, but the nice thing with these the nice thing with simulations like this is you're solving the hydrodynamic equations, which just depends on these basically these laws of physics. Our simulation code also includes, so we use adaptive grids or Cartesian grids for the dust and gas, but we also include Lagrangian sync particles to model stars. So we can form stars when we reach a maximum density or we're on the finest level, and those stars will accrete gas from the surrounding grid, and that will add momentum and that will add momentum to the star particles. Likewise, we also include gravity, of course, because gravity is very important in star formation, and we just do that by solving for the gravitational potential using the Poisson equation. And that takes into account, so all these equations take into account both contributions from the gas and the stars. So with that, we'll show an early simulation where we wanted to see how, if we treat the radiation pressure well, how does that affect accretion onto the stars? Can you still form very massive stars? And so here I'm showing the top panel here shows the whole core. So this is 150 solar mass core. And the bottom panel shows a zoom in of about 8,000 AU, so you can see it more closely. The finest resolution we have is 20 AU, and the core radius is about 0.1 parsec. This corresponds to a very dense core with 1 gram per centimeter squared, which is typical of massive cores. And these two show two different projections. So this is along the I believe the Z slice and then X slice. Oops. Sorry, do that again. So you can see as the star forms, once it gets massive enough, it starts to blow these radiation pressure bubbles away from the star, but material still falls in due to these dense filaments that are due to the initial turbulence of the core. Then eventually you get a significant accretion disk around the star, and that feeds in high density material to the star. But as the star grows and becomes more, and its luminosity grows pretty quickly, you see these radiation pressure bubbles that are expanding away along perpendicular from the accretion disk. So the main takeaway from that is that massive star formation is definitely not a 1D problem. It's a multidimensional problem. And as long as you have an anisotropic accretion flow onto that star, such as in the form of an accretion disk or these end-falling optically thick filaments that fall onto the star, then you can overcome the radiation pressure barrier. Another thing that can also potentially feed material to the star is what's known as radiative Rayleigh-Taylor instabilities. And what these are is basically as these bubbles expand, you have this low density radiation pressure dominated bubbles that's pushing on the surrounding shell of gas. And with time, that shell can actually become unstable and develop these Rayleigh-Taylor fingers, which you can see here, a long finger that can eventually penetrate down to the star. And so the main thing is, you know, like I mentioned, this is not a 1D problem. You need an anisotropic accretion flow. And so, for example, here I'm showing the RAM pressure versus the function of the stellar mass, of the simulation time of these simulations. And what we find is that if you only look at, if you look at the isotropic RAM pressure, you see at about 30 solar masses, the radiation pressure should blow the material away. But if you look at the mass weighted, so this is heavily weighting the regions that are delivering mass to the star, that the RAM pressure is stronger than the radiation pressure and then comes to about 1-to-1, so you can sustain accretion. So it's more about that material accretes into the star in a messy way. So the radiation pressure is no longer a barrier. Sorry, the radiation pressure barrier is no longer a barrier. Now, what about protostellar outflows? So like I mentioned before, these are magnetically launched, collimated outflows from the star, and it's due to the fact that these stars have an accretion disk, and the interaction between the star and the disk and conservation of angular momentum will launch these jets from the star themselves. And we know that this is ubiquitous in both both low mass and high mass star formation. And high mass star formation, because the star formation process is so fast, and these foreign and highly embedded environments, you can sweep up what are known as these entrained molecular outflows. So as the jets leave the star, they can entrain material, and this can actually eject a lot of material from the surrounding medium itself. Also, if you compare the outflow force of these outflows, so this is showing a set of measured outflows from massive protostars. And then this line here is just it's showing the momentum injected by radiation. You see that the momentum added by outflows is stronger than that by radiation. So on a momentum basis, outflows are a very important feedback mechanism. So again, I'm showing the same setup, but now we include outflows. And I should warn too, the velocity dispersion of this core is higher, but the same results, pretty much the same. So you can see the outflows start pretty early. As we look here, outflows are bringing material out. Once the star again becomes more massive, you get these radiation pressure bubbles close to the star, but outflows near the end have ejected a lot of material from the cores.
Anna, can I ask you a clarification?
Yeah.
So maybe I missed the point, but you don't have, these are pure hydro simulation, right?
These are hydro right now. I'll go into magnetic fields in a couple minutes.
So if the outflow is magnetically driven, how is the outflow in
Thank you. I forgot to mention that we modeled the outflows with the subgrid model. So obviously we can't resolve the regions at which these outflows can be launched. So we put in a subgrid model based on observations from the momentum of outflows observed in low mass and high mass star formation, where in a small region around the star, along like a collimation angle, we take about 20% of the accreted mass and then assume a velocity of about 30% of the escape velocity of the star. And then we inject that momentum into several cells around the star, but in a collimated, yeah. So that's, I mean, even with adaptive methods like this, it's still based on computational cost. It's nearly impossible to get down to the launching radius. And to be able to look at, there has been work where they have looked at the launching of these outflows from massive stars. So this is from Rolf Kuiper's group. His former grad student did this, where they looked at how non-ideal magnetic effects can launch outflows or launch jets from the massive protostar. However, those simulations you have to get down to much lower, like sub-AU resolution near the star, and those simulations don't include radiation pressure. So the problem is the most expensive part of these simulations is including radiation. So you have to make assumptions one way or the other. This is something I do plan on. I'll talk to you tomorrow, because the stuff that I'm going to talk about a new framework to do simulations like this, but with better resolution. And so we can look at that in detail at sub-AU resolution, while still having, including radiation and also including non-ideal MHD effects, also including, and then having sub-AU resolution near the star. So this is possible to look at. So the simulations I talked about from Kuiper's group, they use a much simpler geometry for their simulations, like they use a sphere to model the core. And so they can't, for example, model turbulence. They can't, they lose resolution far away from the star and so on. So with a lot of these simulations, you have to kind of cut corners to be able to answer the specific questions you want. So because of the limit in resolution, we have to put in a subgrid model to model the outflow feedback. Yeah, thank you.
Thank you.
But with that, even with the subgrid model, we can look at the overall effects of outflows from these simulations. And by comparing with radiation only, where we do not include outflows, we can look at how outflows actually impact the surrounding core material. So obviously with outflows, you have material that's efficiently launched through these entrained outflows. And then, for example, it also reduces heating because it allows a place for radiation to vent out, because you have these lower density channels that radiation can vent out. And so, for example, if you look at the total, this is the average like core temperature. What we find is that once these outflows break out, the overall temperature of the core itself cools down. And so furthermore too, because these outflows allow radiation to escape and blows out material, you'll also reduce the development of these Rayleigh-Taylor instabilities. So you grow the stars at a slower rate, but also because about 20% of the mass is injected into the outflows. Another important thing too is, well, to include magnetic fields. So the simulations I talked about do not have magnetic fields. And like I mentioned before, the cores and clumps out of which massive stars form are magnetized. Now they tend to be subcritical. So this mass to flux ratio just kind of relates the force of gravity to magnetic pressure, or sorry, gravity to magnetic pressure. And cores tend to be supercritical, meaning that gravity does dominate, but observations suggest by not a lot. And the effect of magnetic fields that it will slow down the collapse and also reduce fragmentation in these cores. So one thing that we find, so now I'm comparing the Popper lines here is including magnetic fields for the same setup. And we can look at how that affects the growth of these stars. So they grow somewhat slower. And you also achieve a smaller accretion disk around the stars. And that can also explain why you get smaller accretion rates onto the star. And that's just because as material falls in, magnetic fields will strip away angular momentum of the infalling material. And so you build up smaller accretion disks and reducing the star's growth rate. It also affects the structure of the outflows and the radiation dominated bubbles around these massive stars. So for example, if we look at radiation plus outflows and then include magnetic fields, we see that when we look at these radiation dominated bubbles, for both cases, they're much smaller in the magnetic case. And that's just because radiation pressure is going to cause material to be blown away, but the magnetic fields, the magnetic tensions actually can confine that. And so if you look at the zoom in for this panel here, what we see is that the magnetic field increases where the gas is being pushed on most. So that actually inhibits the growth of these bubbles. Additionally, the structure of the entrained outflows that should be observed should be different too. So again, when we compare with and without magnetic fields, we see that we still get a messy entrained outflow pattern. And that's just because of the fact that the star itself is being knocked around as it's accreting material. But once you have magnetic fields, you actually get this magnetic levitation effect. So it's easier to push out this material. And this leads to larger collimation angles that can be observed with observatories like ALMA, looking at different molecular line tracers. And so I think that's also why when you see these broadened outflows from massive star forming sites, and this can likely be due to an interaction of these outflows being ejected from the star formation sites, but also interacting with the surrounding magnetic field. Likewise, likewise, and we can do that, we can compare what this volume filling factor is with for both cases. So this is just looking at the total volume of the domain that's covered by these entrained outflows for both cases. And we see that once the outflows start to become really powerful at about 20 solar masses, they kind of overcome the surrounding magnetic field, and you get a larger entrained effect. And that's likely also due to the fact that these cores are collapsing more slowly due to the fact of magnetic pressure. And then finally, we can also look at the mass, momentum, and energy budgets. And so this is how much of the, so looking at these entrained outflows here, because this is going to measure material that can eventually be injected, leading to low star formation efficiencies in these molecular cores that form massive stars. How much is of the injected energy momentum can leave the cores? And this is important for larger scale effects. How much energy and momentum from outflows and radiation pressure is being injected being injected into the surrounding interstellar material that the core belongs in. So what we find is that the entrained mass, so if we look at the launch mass, so this is the total mass injected by outflows, and compare that to the total mass in the entrained molecular part of the outflows, we find that the entrained mass increases by a factor of 3. And so that leads to lower star formation efficiencies, because that mass will be ejected from the core. Likewise, we can look at the ratio of the momentum and energy of the material, of the entrained material, and we see that varies roughly for the momentum and kinetic energy is about 25% to 5%. So this is saying that all the momentum and energy that's being put in near the star doesn't necessarily leave the core. And so, for example, and let's say larger scale simulations, you can overestimate. If you assume 100% of the energy that is put in leaves the immediate environment, then, or by immediate environment, I mean like the core itself, you'd be overestimating this. So this has important implications for stellar feedback on the surrounding scales. Likewise, outflows are very important for studying the star formation of massive cores. So this line here for 33% is what's observed for low mass star forming cores. That says about a third of the mass goes into the low mass star. whereas for massive stars, observation suggests it's about 40%. If we do not have outflows, then you would achieve star formation efficiencies that are too high. So it's really the outflows that are setting the low star formation efficiencies and not necessarily radiation pressure for the that are observed. And then likewise, and this is going back to your question about modeling the outflows, this is a good consistency check, because we find that the outflow force as a function of the source luminosity matches what has been observed. So in this modded sample, so this bone top sample is what it is a power law dependence for what's observed for low mass star formation, but you see a shallower slope for high mass star formation, high mass star formation. And our results agree quite well with that. So even though we use a subgrid model, we do get the momentum right so that we can model the overall outflow force in these entrained outflows accurately. And I'll finish up with talking about stellar winds. And like I mentioned before, stellar winds, this is for massive stars, these are winds that are radiatively launched. So because the radiation from the stars are so high that the material, mostly like iron and other metal ions in the atmosphere, are highly opaque. And so the absorption of radiation and the outer layers of the star will push out material. And that material has to leave the star at above the escape speed, which is about, around 1,000 kilometers per second. And so these are really fast stellar winds. They range between 10 to the -8 to 10 to the -6 solar masses per year. And this happens when the star is very hot, so above like 10,000 Kelvin or so. And as those winds leave the surface of the star, they're going to collide with surrounding material, and you're going to get this shocked stellar wind. And this shocked stellar wind will produce low density gas that's at millions of degrees Kelvin, and this gas will then adiabatically expand. And so the hot gas pressure can push out a lot of material. And so when we include winds in addition to radiation and outflows, what we find is that winds can actually, and these low density channels that are carved out by the radiation pressure and outflows from the stars themselves, the hot gas will adiabatically expand and engulf those regions. But you can see the areas along where the accretion disk is, that area is still shielded. So you don't cut off the accretion flow, but you lower it. And winds occur when the star is sufficiently massive, around 20 solar masses, because the star itself has to be quite hot to be able to launch these winds. And so when we include winds, in addition to these other feedback components, that reduces the accretion rate onto the stars themselves. But now again, if we look at magnetic fields, when we include that effect, what we find is that because of this magnetic confinement effect that I talked about before in the context of radiation pressure, you see that it has a smaller effect. You don't get these broad regions of hot gas that can adiabatically expand. And in fact, what you find is that you actually get this increase in the accretion rate onto the star that then starts to decrease. And so at first that seemed, counterintuitive. But once you look at it at comparing the magnetic to the thermal pressure, it made a lot more sense, because these winds and then the hot gas that it will produce is going to push on the magnetic fields, and due to flux freezing and that will increase the magnetic tension. The magnetic tension is going to push back and not let those regions expand. Eventually, once the winds are strong enough, then they could have more of an effect, which is why you see the accretion rate start to drop. So the mass growth of the star starts to slow down. And so what this suggests is that stellar winds, unlike radiation pressure, can be quite important at late times. So just to recap, before I go into the end of my talk, where I'm going to talk about some new stuff that we've been working on. The first thing I want to talk, just, you know, like I said in the beginning of my talk, it's nice to kind of look at this on going through the different feedback mechanisms to really get the intuition to see how each feedback mechanism works together. So in the context of radiation pressure, we find that radiation pressure is not enough to stop the growth of massive stars. For example, we get up to a 60 solar mass star in the simulation with the radiation pressure alone. And that's because we get an anisotropic accretion flow due to these dense filaments that are due to the initial turbulent structure of the core itself that can bring optically thick filaments to the star. You also get these Rayleigh-Taylor instabilities that can be important at later times as the shells that expand, these radiation pressure driven bubbles expand, they become unstable. And then finally, you also build up a significant accretion disk, very dense accretion disk. And so that shields from the radiation field and you accrete most of your material that way. Likewise, when you include outflows, you see that outflows are necessary for the star formation efficiencies observed. They eject about a significant fraction of the material from the core itself that cannot then be incorporated into the stars. And then likewise, when you include magnetic fields lead to smaller accretion disks due to magnetic braking, but also to these wider, less collimated outflows due to the fact that you get this magnetic levitation effect because the core itself is more slowly collapsing. And then finally, you require outflows in addition to radiation pressure to actually set the star formation efficiency, but also get the correct entrained outflow energetics for these massive star forming cores. So radiation pressure alone or radiative feedback alone is not enough to stop accretion onto massive stars. Likewise, once you include these stellar winds, in the case of no magnetic fields, you see that winds can be quite effective at slowing down the growth of these stars. But when you include magnetic fields, it weakens that effect because early on you suffer from this confinement due to magnetic tension again, which reduces their effect. And so the stars themselves need to be more massive for winds to start to become more effective because the winds will be stronger at higher stellar masses. So I'm just going to use the last few minutes to talk about a new project that I'm on, and that's kind of directing the next few years of my research focus. And this is to continue studying massive star formation on small scales, but also on larger scales. And so I'm going to briefly talk about the star formation and gaseous. Sorry, I don't know if you guys heard that. Star formation in gaseous environments. This is a new framework based off the Gizmo MHD code, meshless simulation code that was developed by Phil Hawkins. And the nice things about this new framework is it's the first of its kind that includes all the relevant feedback processes and can also resolve individual stars. So for example, in the simulation that I showed above, where we only look at cores, is because it's too expensive to be able to go from the size of a giant molecular cloud down to the size of, tens of AU where you can, resolve star formation. And so this is a nice framework because it uses a different method for the MHD, you can actually achieve much higher spatial resolution to be able to form stars. So with this code, since we can form individual star formation and we include MHD, we can also look at the n-body dynamics of stars. We can include the different processes I discussed above, and then also include supernovae to really look at how stellar feedback affects the formation of star clusters and the disruption of molecular clouds. And now, since we can actually resolve individual star formation, we can actually study the dynamics of these star clusters. So here I'm showing a simulation of a dense GMC, 10,000 solar masses, where we had massive stars form. And each dot here is an actual star. Most simulations to date all simulations to date that include all these feedback components, they can't resolve individual stars. They instead have to do these mini star clusters. So they have to put the IMF in by hand and then make assumptions about the other properties of the stars. So this is the first of its kind where we can study individual star formation on GMC size scales. So for example, we can look at the dynamics. Here's an example of a star cluster in Orion, where Swigum et al. Looked at Gaia data to determine that the star cluster is actually expanding. Likewise, if you include dust emission of the gas surrounding the star cluster, you see that there's this dust shell around it, suggesting that feedback is responsible for the expansion of the star cluster. And so one thing that I will be exploring is how does the stellar dynamics of star clusters in GMCs depend on stellar feedback, the star formation efficiencies, and also the GMC properties. So we can study this type of problem in exquisite detail. Likewise, we can look at the initial mass function. So one of the biggest questions right now in both the Milky Way and outside the Milky Way is the initial mass function actually universal? And how does stellar feedback set the initial mass functions of the distribution of stars? So here I'm showing the initial mass function and comparing it with theoretical models from Krupa and Chabrier. And the histogram shows the stars formed in this simulation here at the last snapshot. And you see that it fits the observed IMFs very well, but we do see this high mass end here. And like I mentioned before from my previous simulations, this could suggest that winds, in addition to radiation pressure and outflows, set the higher mass stars. Work by David Gushinov, he found that, for example, outflows sets the peak in the low mass end, but you require more feedback physics, so radiation pressure and potentially other forms of feedback to control the high mass end. And I suspect that winds are going to be very important there. Additionally, by doing this for a variety of giant molecular cloud properties, we can look at how does the metallicity feedback and the initial properties of, or initial conditions of these GMCs actually affect the IMF to determine if the IMF should be universal. Another thing too is to look at the importance of different feedback mechanisms. So one example that has been looked at by myself and others throughout the years is the importance of this wind feedback. So if we look again at 30 Doradus, we see that a lot of gas is evacuated by this hot gas that's generated by the shock heating of stellar winds. However, if you look at the components, if from this X-ray emission, you can determine what the properties of this hot gas is and compare it to what you expect the wind energy is injected throughout the cluster's lifetime, and you find out that there's a lot less energy in this hot gas, suggesting that winds are not as important as we think they might be. This is assuming that all the wind energy is not transferred to pushing on the ISM. And so there's other ways that wind energy can be lost. And so we can look at that with these simulations to really determine how important is wind feedback. And then finally too, one last thing for us to look at is cosmic ray feedback. And so cosmic rays, and I'm focusing on cosmic ray protons right now, these are going to be accelerated by the shocks from stellar winds and accretion shocks and so on. You have these fast shocks that can accelerate particles to relativistic speeds. And there's been several simulations throughout the last several years looking at the effect of cosmic ray feedback on galaxies and launching outflows from galaxies. However, we are now seeing strong gamma ray emission. So you receive this gamma ray emission. This is an observation from Laura Lopez, using Fermi data to look at the gamma ray emission. And 30 Doradus, and you see it's quite gamma ray bright. And that's because these gamma rays are due to the fact that cosmic ray protons will collide with the dense interstellar medium and transfer energy, transfer momentum to the interstellar medium. And when you have this collision, you produce pions that then decay into gamma rays. And so this suggests that even on the size scales of star clusters, cosmic ray feedback may be quite important. And then finally, from those two things, we can also consider, well, by modeling cosmic ray feedback and wind feedback, we can look at what is the escape fraction of cosmic rays and the shock heated gas by stellar winds. And so that we can then use that to develop better subgrid models for cosmological and galaxy formation scale simulations. And the last thing I'll mention is with these simulations, we can also compare directly to observations. So we can post-process these simulations. Here's an example from Grace Olivier, who's a grad student at OSU. We put out a paper where she looked at the different feedback components for stellar winds, radiation pressure, the warm ionized gas. And so we can use these simulations to directly compare, to look at the evolution of feedback in H2 regions. And then finally, also look at, by zooming in on these, we can also look at how does accretion happen onto the sites of massive star formation? Is it a dynamical process? And what are the properties of these massive starless cores? Do these virialized cores exist? So I'll end there with the same recap, but just wanted to show you guys some new exciting stuff. Thank you.
Thank you very much, Anna. I'm gonna clap for everybody here.